Alright, section 3.1 is about thinking about derivatives as a function. So we talked about the slope of a tangent line to a curve at a certain point, but we are going to introduce in 3.1 the concept that derivatives are a function. We'll also introduce you to a new form of the difference quotient, so you can see that as a limit. And we're going to think about how derivatives relate to the function for which they are the derivative. Okay, so first a definition. A derivative, which is written f with a tick mark next to it, so f prime, is a function. The input is the x-coordinate of f, and the output is the slope of f at that point. So if you have a derivative function, you can input any x-coordinate and figure out what the slope of the original function was at that x-coordinate. So one of the things you have to be able to do is sketch a graph of f prime based on what f looks like. And so some things to think about as you're making that sketch. You want to think about where the graph has horizontal tangent lines. So where you notice horizontal tangent lines. Because if you see a horizontal tangent line on your f graph, you know that the derivative would equal 0 since the slope of a horizontal line is 0. So all of these are the zeros of the derivative graph. Just based on that, it should be pretty easy to match up these graphs. But the other things I want you to think about as you're looking at f graphs and trying to sketch a graph of f prime is where the graph is increasing. If the graph is increasing, that means that the derivative would be above the x-axis. You also want to look at where the graph is decreasing, because when the graph is decreasing, the graph of f is decreasing. That means the graph of f prime would be below the x-axis. So with those things in mind, you can match these graphs fairly clearly. So this is an increasing graph all the time. It's also a horizontal line. It's also a straight line, which means that the derivative would be a horizontal line with the matching slope. So the slope of this is a rise of 1, a run of 1, and there's a horizontal line at 1. Any x-coordinate would give you a slope of 1 for that particular graph. The derivative of this graph would always be positive, so it would always be above the x-axis, and it would have a 0 at 0. Oops. This graph has a lot of zeros, and also the increasing, decreasing behavior matches the above the x-axis, below the x-axis behavior of that graph. This graph happens to be a graph of the sine function, and the derivative of that is the cosine function. That's something that we'll come back to later, but that's the matching for those. So here's a summary of how to sketch a derivative graph if you're given a function. The first thing you want to look for is horizontal tangent lines, which are also maximums and minimums, or often are maximums and minimums, so you might look for maxes and mins. So if I were to sketch the derivative of this graph, I would know that there would be a 0 a little bit before -1 and a little bit before 1. And then I also want to look for periods of increase and periods of decrease, because I want to correlate that to above the x-axis for the derivative graph. So this section of the derivative graph should be above the x-axis, and below the x-axis, or decreasing would be below the x-axis, and then increasing would be above the x-axis. So if I were to sketch this, it would look something like this, And I don't know exactly how low it would go, but that would be the shape I'd be going for. Here's an actual sketch of the derivative. I guess it's off the screen a little bit, but it would look like that. So if you think about these 4 functions, one of them happens to be the derivative of itself. And if you think about what we've already talked about with slope and derivatives, you should be able to tell which one is a derivative of itself. For example, this one is showing you that it has a slope of 1 all the time, so its derivative graph would always be above the x-axis, and this one is not, so this is not a derivative of itself. This function is also always increasing, so its derivative would be always above the x-axis, and this one drops below the x-axis, so this one doesn't work. This graph is always increasing, and it starts off not very steep, and then it gets steeper and steeper and steeper as the y-coordinate gets bigger. So the graph of e to the x is actually a derivative of itself. At each point on the graph of e to the x, its y-coordinate is also its slope. Kind of blows your mind. We'll come back to that idea as well. You don't have to memorize the derivative of e to the x at this point, but it makes sense looking at the graph that it's true. Okay, so we've talked about derivative being a function. If it's a function, we should be able to graph it, but we should also be able to write an equation for it. So in chapter 2, when you were finding the slope of a tangent line, it was always at a single point. But we can also figure out what the derivative function is for any function. So we can use that same limit that you used in chapter 2 to figure out the derivative function. The key is we're not going to plug in a number until we get to the end of our calculations, because we want to figure out what the function is, and then we can plug in the number later. So if you want to pause the video so you can try this yourself, I'd recommend that you do that, but I'm going to walk you through how to do this. So f prime at a is going to be square root of, it's going to be the limit as h approaches 0 of the square root of a plus h minus the square root of a all over h. And what I notice is that I'm kind of stuck. I know this, if I plug 0 in for h, I get 0 over 0. So there is some factoring I can do, and so noticing that there are square roots in the numerator, I'm going to try to just rationalize the numerator by multiplying by the conjugate pair. So I'm going to multiply by root a plus h plus root a all over that same thing. So I'm going to do that. And that's because that's a conjugate pair. So then when I do that multiplication, I get the limit as h goes to 0 of a plus h minus a. And I'm not going to actually distribute the h. And what I notice is that these a's subtract to make 0. And now that there's nothing left in the numerator except for an h, these h's divide to make 1. So I'm left with, after simplifying, the limit as h goes to 0 of 1 over square root of a plus h plus square root of a. If I plug in 0, I now can come up with the function that is the derivative. So I have square root of a plus square root of a, so I have 2 square root of a. And the reason for that was h went to 0. This is the function for the derivative. You can spell that with an x if you'd rather. It'd be 1 over 2 root x would be the derivative of the square root of x. If I plug in 100, so f prime of 100 would give me 1/20th as the derivative at that particular point. But the value of having a function is that now I can figure out quickly the slope at any point, not just at one given point. There is another derivative definition that I want you to be able to recognize, and I want you to notice that this part is the slope formula between 2 points. So this is called the difference quotient, remember, in calculus, so we call that the difference quotient because it's basically the slope formula. And then there's a limit, and the limit is bringing those 2 points infinitely close together. The x-coordinate is getting closer and closer to the a-coordinate, which means that these 2 points are really the same point as we approach that limit. So I'm going to show you how this alternate definition works for the same function, so you can kind of compare how they work. They both give you the same answer because they're both giving you the derivative. So if I take f prime of a of this new method, I would have the limit as x goes to a of f of square root of x minus the square root of a over x minus a. And again, I'm going to multiply by the conjugate pair. So this, you notice, is very similar. You may have a slight preference, and you're welcome to use either one, but you have to recognize both of them, so you're not off the hook for recognizing either one of them. And then I'm not going to FOIL out my denominator, because if I don't FOIL it out, it's easier to see that my x minus a's cancel and make 1. So x minus a over x minus a equals 1, and so I'm able to cancel those out. So then I have the limit as x goes to a of 1 over root x plus root a, and now x is going to a, so I have 1 over 2 root a, which is the same answer that I got in the previous problem, because they're both the derivative. What I want you to know is that on the AP test, sometimes they'll give you these difference quotients, and they'll expect you to recognize these limits of difference quotients, and they'll expect you to recognize that they're really asking you for a derivative, so you don't, on the AP test, wind up doing a lot of work with limits, because if you recognize it's a derivative, eventually you're going to have shortcuts for solving those problems. So anyway, f prime of 100 would still be 1 over 1/20th, because it's the same derivative function. So if you're given a table and you need to figure out, because functions can be expressed as a table, if you're given a table and you need to figure out the derivative, then that's just a fancy way of saying slope. So if I want to figure out, so this is the probability that people in a room have the same birthday. If I want to figure out the rate of change of the probability, or the slope of the probability, then it's really just a matter of finding the slope between 2 points. The reason this is a 2.5 is because I'm between 0 and 5, and if I have a table, that's not the slope at 0 or the slope at 5, that's kind of the average slope between them. So we're going to use the midpoint and say, okay, if you have 2.5 people in the room, the rate of change of the probability of the shared birthday would be 0.027 minus 0 divided by 5, whatever that is. And that's going to be the rate of change of the probability of the birthday. And etc. You could do the same thing for 7.5. You're just doing the slope formula between 2 points to figure out the rate in a table. Since this is a function, I just want to really emphasize that it can be expressed in a table form. So here's a summary of section 3.1. Since a derivative is a function, you can see it as a graph, equation, or a table. The input is the same input as f, so the input is going to be the x-coordinate, but the output will be the slope of f at x. All right, good luck with 3.1.